Alright, so in this lecture, I will be talking about BERT. Hopefully, you're now ready after watching my lecture 3 and 2 and 1 about language modeling, how these ideas are evolved, and now you're ready for BERT. And in part 5, I will implement BERT in PyTorch, and in part 6, I will use the transformer library to work with different functionalities of BERT. So let's start with the original paper of BERT, written by amazing scholars. And this is the original article of BERT in 2019. And there are also very great articles like OpenAI, GPT, and Roberta. And there are many variants of BERT because you can train it on different, for example, if you train it on scientific corpus or if you train it on biomedical text. So there are many versions of BERT because it depends on which corpus you are training, and there are slight modifications on that. So the language model pre-training has been shown to be effective for improving many natural language processing tasks. These include sentence-level tasks such as natural language inference and paraphrasing, which aim to predict the relationships between sentences by analyzing them holistically, as well as token-level tasks such as name entity recognition, question answering, where models are required to produce fine-grained output at the token level. So there are two main strategies, either like previous lecture that I explained ELMO for word embedding, and I used that bilanguage model, bidirectional language model, and ELMO, which was feature-based. And this lecture, which is about, and also fine-tuning. For fine-tuning, it's like part 2 of my playlist, Universal Language Model. And of course, it's like generative pre-trained transformer, the OpenAI GPT, and some articles that I will explain later. So what is the comparison? You see, in comparison, BERT, in OpenAI, I will explain it at the end of this lecture, but this is the architecture differences in pre-training architecture of ELMO, my previous lecture, OpenAI GPT, and BERT, which is this lecture. So BERT representation are conditioned on both left and right contexts. So this is very interesting. And so we argue there is limitation. The standard language model is unidirectional. So we argue that the current techniques restrict the power of pre-trained representations, especially for the fine-tuning approaches. So the major limitation is that the standard language models are unidirectional, and this limits the choice of architectures that can be used. For example, OpenAI GPT, which everybody loves, the authors use a left-to-right architecture, where every token can only attend to previous tokens. So such restrictions are suboptimal for sentence-level tasks and could be very harmful when applying fine-tuning based approaches to token-level tasks such as question answering. So BERT is bidirectional, and for that we use masked language model, MLM, masked language model. And BERT is bidirectional representation, encoder representation of transformer. So if you've seen the architecture 2017, here BERT is just the encoder, 12 layers of encoding. And this is BERT. So BERT is bidirectional. We use mask mask language model. For example, I will explain it in another slide. For example, CLS, this is for classification. So the first corresponding one is, for example, what is next sentence prediction or any classification things that you need. So it's next sentence classification. And for example, we can give two sentences by using separator. And we use masking. For example, just mask one of these tokens and see what is the response. And so this is pre-training. For pre-training, we use I will explain them separately. So fine-tuning is after pre-training. And fine-tuning, so depending on the task, for example, if you're using Squad database, which is for question answering, if you see my playlist for question answering, 10 lectures, or if you see name entity recognition task, I have explained this in my structured prediction in my CRF conditional random field playlist, or any other task. So you can use different tasks for fine-tuning. So as I said, it's a paradigm. First you do pre-training and a big corpus, for example, and then you fine-tune it. You do domain adaptation and focus on a specific corpus, probably what your domain you're working at. And then, so it's a paradigm, and then you test it. So this is the BERT. First with pre-training, as I said, for example, you omit some token, for example, token 2, and you predict, you see what is the probability of occurring that. And then for fine-tuning, you use different tasks, for example, squad dataset for question answering, name entity recognition, and so on. So the model architecture, first of all, we are using the encoder. BERT has 12, the default is 12 layer, and the number of hidden states, you will see that when I coded in IntelliJ, when I coded in Python, in PyTorch, you will see that it has 768. The default of that is this is hidden size. And so total parameters is 110 million. But BERT large has 340 million parameters, which is quite big. So BERT architecture is a multi-layer bidirectional transformer based on 2007. This paper, I've explained this paper several times in my YouTube channel. And then, so my personal idea about our brains is that, in software, I was software architect, 8 years ago exactly. So I used to be a microservice architect. I love microservice architecture. And monolithic architecture is like our deep learning, even in 2023. So everything we want to do it, I don't know why we want to do it all at once. But human brain is very narrow. It focuses on the specific task and uses different parts of the brain, not all of the 100 million billion neurons of your brains. And so it's like microservice architecture. So our brain is like microservice architecture, but the community of machine learning is in deep learning that we develop is like monolithic architecture. That's why you have problems for scaling. That's why you have problems of curse of dimensionality. That mathematicians don't have problem of curse of dimensionality, but machine learning engineers have, because their paradigms are tragically different, dramatically different. So let's come back to BERT. BERT base was chosen to have the same model size and OpenAI GPT. So BERT transformer uses bidirectional self-attention, while GPT transformer uses constrained self-attention. And every token can only attend to its left, so it's not good, but BERT is good. Bidirectional is very nice. So to make BERT handle a variety of downstream tasks, our input representation is able to unambiguously represent both a single sentence and a pair of sentences. As I said, we separate it with this token, and so that's it. We separate two sentences with separator, and CLS token is, I think it's number 112, the index of that, and 101 maybe. And so the first one is CLS, you see here for classification, and the rest of them is for language modeling. For example, if you mask this token, the corresponding that you can predict, for example, what is the probability of each of the tokens of your vocabulary. Depends on your vocabulary. So we use separator, so I said everything, and input representations. So we have a complex input representation because it's sum of position embedding. We will implement all of them in PyTorch. Position embedding, what is the position? Is it the second? A segment embedding, is it sentence A or sentence B? For B, all of them is B. So it's a simple, segment embedding is very simple. And token embedding, for example, each one, the usual standard way. For example, for CLS, we use a token, different tokens for different words, and then we add them up. So the pre-training BERT has two parameters. So we can add, when you implement it, we can add them. We add the loss because we have mask language model for pre-training and also next sentence prediction. So we have two tasks. So task one, as I said, is just mask language model. And so I've said everything here, so nothing important. So in pre-training BERT, if you're using BERT base from left to right, because you can use it different ways, you see the accuracy is less than when you're using the mask language model. So you see this mask language model, the upper one, has higher, this mask language model has higher accuracy. And so for next sentence prediction, you have a sentence, what is the next? Is it the next sentence? So it's a standard classification. So we have two labels. Is it is next or not next? So it's very simple classification. And finally, you go to fine tuning. Fine tuning, is straightforward since the self-attention mechanism allows BERT to model many downstream tasks. So example of mask language model, as I said, for example, my dog is Harry, my dog is, we don't know what is the next word in language model, we want to know what is the next word, and then even you see many amazing things for story generation, all of those things are because of these incredible transformer architectures. For example, here in BERT, we only have encoder and we just generate it. So we mask any word that we don't know and we predict it. So 80% of the time we replace the word with mask, as I said, but 10% of the time we replace the word with just a random word in your vocabulary. And the remaining 10%, we keep the word unchanged. So example for next sentence, so we have a sentence, we start with CLS, the man went to mask, and then we use separator. And a separator, it means that the next sentence, after that the next sentence. And because if this is this next sentence, it is next. So is next is one. But if it is not next, so it's not next. And so it is can be used for sentence prediction. So sentence pair classification task. So as I said, there are many data sets. For example, in the problem of multi-genre natural language inference, this can be used for that. Or Quora question pairs is a binary classification We want to know, are they semantically equivalent or not? And the next one is question natural language inference. You can use all of these things because you're doing classification, sentence per classification. And of course, you can do textual similarity. You can use the Microsoft Research paraphrase corpus, automatically extracted from online news. For whether the sentences in the pair are semantically equivalent or not. Because two sentences may be very similar to each other. We can take advantage of BERT here. So RT is another thing. Recognizing textual entailment is a binary entailment task. And for single sentence classification, you just use, for example, what is the class label of that? For example, if you're using the tree bank of Stanford Sentiment Tree Bank, which I really like, it's a binary single sentence classification. Or if you're using the corpus of linguistic accessibility, it's a binary single sentence classification. So you can use BERT as well. But you can also use it for question answering. Because if you see my playlist for question answering, they have used BERT in one of the papers that I've explained. So we give the question and the answer is inside this paragraph. We don't know where, but we find the start and end span of the answer. So we learn that. But the reason I don't like this approach is because it's just memorizing, I love semantic parsing. I've written an article about semantic parsing, but my next two articles are about semantic parsing, and I love semantic parsing just because it's really natural language understanding, and it's not memorizing anything. It's really parsing, because our brains, we parse, therefore we exist. I believe that we parse, therefore we exist. So even a dog can parse, so it can do reasoning. The reason that it cannot do that because the dog doesn't have enough words in his or her vocabulary, and because it doesn't have enough words, it cannot do reasoning as complex as human. So the next application is single sentence tagging. These beginning person, these name entity I have explained this in my CRF playlist, conditional random field, because, before BERT, we used to work on CRF, conditional random field. Of course, nowadays we can work with a combination of them. There is no conflict between them, but some people say that, argue that we don't need conditional random field for tagging because BERT can already do that, but I don't agree. So the first token is CLS and then token 1 token. So it's a single sentence, and for each of them, the name entity recognition. So the name entity of that. Or even if you're doing part of speech tagging or any kind of tagging that you have, you can take advantage of this. You can train this and take advantage of it. So let's compare BERT, Elmo that I explained in my previous lecture, and OpenAI GPT. So GPT BERT is trained on books corpus, 800 million words. GPT uses sentence separator and classifier token, which are only introduced in fine-tuning. But BERT learns separator and CLS and sentence AB embedding during pre-training. And GPT was trained for 1 million steps with a batch of 32,000 words. BERT was trained for 1 million steps with a batch size of 128,000 words. GPT used the same learning rate. For BERT chooses a task-specific fine-tuning learning rate, so a slight modification.